So welcome everyone to the evening session of the workshop. The first speaker of the session is Geoff Penington from UC Berkeley, and he will tell us about non-isometric codes and the black hole interior. So Geoff, please start.
Okay, well, thank you very much for inviting me to talk. So I'm planning to talk about a paper that came out in July with Chris Akers, Netta Engelhardt, Daniel Harlow, and Shreya Biden. And the title is something similar to what I call the title of the talk, something about non-isometric codes in the black hole interior. And I think maybe complexity gets mentioned in there. So this is it's a long paper. I think it's 100 and something pages long. Goes into a lot of technical calculations, and I'm not really going to talk about any or many of them, but I want to give you guys some flavor of the spirit of what this paper is about, what we're trying to do, what we think we've achieved, and so on. So the real motivation for the paper starts with this result that I guess now is pretty well known in 2019, where various of us were able to derive for the first time the page curve for Hawking radiation, basically by just taking the ordinary semi-classical Hawking calculation that supposedly gave the wrong answer, that supposedly showed information being lost, and applying the so-called quantum extremal surface prescription, the QES prescription, so the quantum generalization of the Ryutaki-Nagi formula from ADS-CFT that was originally used to calculate entanglement entropies in ADS-CFT and applying it to the case of an evaporating black hole. So this was obviously pretty exciting. We've wanted to derive the page curve for a while, but there was a common complaint at the time, or confusion, or people, just unclear about what exactly was going on here, which was that our derivations used the Hawking state, this semi-classical state that was supposed to be wrong, that was supposed to give the wrong answers for everything, and yet somehow we ended up deriving the right page curve for the entropy. Okay, and there's been a stronger form of this complaint being given by various people more recently from sort of other communities and so on, that have basically said, look, you're not computing an entropy at all here. You have some state that has an entropy that doesn't follow the page curve, and you're just making up some different quantity that involves this area plus entropy of some extremization procedure that does follow the page curve, and then you're declaring victory, but you haven't done anything at all because the actual entropy isn't following the page curve. So I don't think that strong version of the critique is right at all, and in particular, at the end of 2019, there were two papers that came out, the so-called East and West Coast replica wormhole papers, that sort of clarified to a large degree why that critique is not right and what these calculations are actually doing. So mathematically, what is happening here is that really the computation being done is a so-called replicatric computation, where you compute so-called trace of rho to the n, you compute some quantity on multiple copies of the system, and that quantity actually involves geometries that contain so-called replica wormholes, which are wormholes connecting the different copies of your geometry. And then you do a mathematical analytic continuation of that answer in order to get an entanglement entropy. And the only role of the Hawking state in that calculation is that when you do the analytic continuation, you end up with something that almost looks like there's no replica wormholes. And the Hawking state is the state the bulk fields would be in if there were no replica wormholes, but actually it does. And so the Hawking state is just sort of a mathematical tool that's relevant to the computation, but it's not actually the relevant state being described. Like you're not getting the same answer you would have had the Hawking state because there are these replica wormholes. So the Hawking state is the answer you would get if we were just doing, say, quantum field theory in curved space-time, where there'd be no replica wormholes, but in quantum gravity, you do have replica wormholes, and so you just get a different answer, and it's just a tool in the computation. Okay, so just to be a bit more explicit about that, what these page curve calculations are really computing, and hopefully this story will be relatively familiar to at least a large number of you, is what's Maxfield and Maroff dubbed the swap entropy, which is imagine we take n copies of a system and we want to compute trace of rho to the n. Okay, if we have n copies of rho, then trace of rho to the n is actually the expectation value of an observable on those n copies of the system. It's just an observable that cyclically commutes the n copies of the system. Okay, that trace of that permutation operator times n copies of rho is the same thing as trace of the n to power of rho. This is some formula that's analytic in n. And so in principle, if we know the answer for all values of n, we can analytically continue to non-integer values of n. And then if we go to n equals 1 and take the derivative at n equals 1, then we get an answer that in ordinary quantum mechanics would be an entanglement entropy. Okay, in quantum gravity, maybe it's more complicated. But that is, this analytic continuation is the analytic continuation of some observable expectation values on multiple copies of black hole. And that's the thing that we're computing and showing based on this page curve. Okay, so to some degree, that answers all these confusions up here. It's a very concrete thing that says, look, this is the observable we're computing. This is how we're interpreting it. This is how we get from that to an entanglement entropy and so on. But there's also various things about it that are kind of unsatisfying. And the big one is, okay, if the Hawking state was just a intermediate step in this mathematical computation, then is that all it is, or is it not? Okay, is it really just a mathematical trick that we use, or does the Hawking state actually have some sort of physical interpretation? Does it play some physical role in the computation, even if it's not the sort of real state that we want to be computing the entropy of and seeing that we get the page curve? And sort of either conclusion here leads to a host of other questions. In particular, if the answer is just A, that the Hawking state was just a mathematical trick, then should we believe in the black hole interior at all, or is the entire black hole interior just a mathematical trick that we can use in computations, but doesn't physically exist? Is there really secretly a firewall after all? On the other hand, if the Hawking state is physically significant in some way, if we're supposed to believe in it to at least some degree, then how are all the arguments for firewalls, so the AMPS argument, the Mathur small corrections theorem, and so on, evaded if we have explicit computations that say somehow on the one hand you have the Hawking state, and on the other hand you have the page curve? So one response that people like Mathur have made is that secretly there must be some non-local dynamics going on here that we're putting into the system or that we're using. As I say, I don't think this is the answer. I very strongly don't think this is the answer, but that's one response people have made to I think, a genuine confusion here, or a genuine thing that needs to be clarified. Okay, so I don't think we know whether the answer here is A or B. I think it would be very hard to know because it's sort of less a question about the mathematics of quantum gravity and more a question about how you interpret that mathematics into observable experiences. And that sort of is hard to determine without jumping into a black hole yourself. But what I will be doing for the rest of this talk is assuming option B rather than option A. Okay, so I'm going to assume that actually the Hawking state is going to play some physical role, that it's not purely a way of calculating entropies and stuff that doesn't really exist, and that's really just a firewall. And there's sort of two reasons for doing that I think are justified, even if they're not conclusive in making us believe that it's really definitively right. The first is the original reason, going back to Hawking arguing for information loss, that semi-classical general relativity seems like it should be valid at the horizon. And semi-classical general relativity says that the state of the horizon should be the Hawking state. And so it seems like we need some pretty good reason to throw that out. Like maybe it's wrong, maybe there's some new physics that comes into play. But we should only expect that to be the case if either we see strong signs of the new physics, or there's some really strong paradox that says, no, it can't possibly be right. And the fact that we now have computations using the Hawking state that do give the page curve and so on, and as I'm going to explain in this talk, the fact that it can sort of make sense for the effective state to be the Hawking state, I think means that we should be unwilling to start believing in firewalls unless we really have to. The second is a more general statement about how we think about ADS-CFT. So we've been familiar with the Ryotaki-Nagi formula and the QES prescription and ADS-CFT for a while. And we don't normally think of them as just mathematical tricks where you're using some state that isn't the real state, but then doing computation that gets you correct answers, right? We normally think of the bulk as being physically real, not just the boundary being physically real. And the bulk is supposed to emerge out of the entanglement structure of the boundary state and so on. And so the RT formula and the QES prescription are meant to be telling us about the real physical bulk geometry. And in the case of a black-braiding black hole, they want to describe the bulk geometry where there's an interior and there's the Hawking state and so on. And so it seems like it's something we should be taking seriously. And so that's what I'm going to do in this talk. I'm going to try to understand how Hawking's effective field theory calculation can be consistent with a fundamental description that has a finite entropy given by the Bekenstein-Hawking entropy, and that is unitary and follows the page curve and so on. And just how to reconcile those things, see what we have to give up compared to our usual ways of thinking about effective field theory and what we're able to keep. And in particular, I just want to illustrate this with really concrete toy models. So no sort of appealing to Euclidean gravity black box calculations where we sort of get out these answers, but we don't really know what the theory was doing to get there. We're just going to be dealing with very concrete qubit toy models, and we're going to see all these features appearing in that. So hopefully that will at least make it clear, even if you still want to believe in firewalls, it will at least make it clear what you have to give up to avoid them and what the alternative is where you don't have firewalls. Because I think this is sort of the unique alternative. I think, over the last 10 years, sort of all this stuff has coalesced into one consistent alternative story to firewalls. And it involves some radical stuff, certainly giving up a lot of things that we assume to be true. But there is a nice consistent story there. Okay. So let's just start with ordinary ADS-CFT. No black holes. Let's just think about, say, perturbations around the vacuum state, like low energy states that we can think of as approximately bulk QFT in a vacuum ADS background. Okay. So in this context, we learned from Almiri, Dong, and Harlow, close to 10 years ago now, that the nicest way to think about ADS-CFT is as a so-called quantum code. So what do I mean by that? Well, I mean that we have a set of states that are called H-bulk, the sort of bulk effective field theory Hilbert space, that is basically the Hilbert space of low energy bulk quantum field theory modes in this fixed geometrical background. Okay. And then there's the so-called holographic map V that tells you how those states get related to boundary CFT states, specifically low energy boundary CFT states. The CFT Hilbert space is morally a tensor product of different boundary points, Hilbert spaces at different boundaries points. And we can think of those as like the logical state and the physical state in a quantum code on some quantum computer or something. Okay. And crucially, this map V is always thought to be an isometry. So what does that mean? It means the V dagger V is equal to the identity on the low energy effective field theory bulk Hilbert space. The inner products in the bulk are the same as inner products in the boundary. Orthogonal states in the bulk are orthogonal states in the boundary. I say isometry rather than unitary because we're mapping a smaller bulk Hilbert space here into a larger boundary Hilbert space. And so VV dagger is not equal to the identity. VV dagger would be a projection onto a subspace of the boundary Hilbert space that describes these low energy bulk states. That's often called the code subspace. Okay. So in fact, this quantum code has interesting quantum error correction properties. So what I mean by this is that even if we lose access to part of our boundary Hilbert space, some subsystem of our boundary Hilbert space, so say we only have this sort of left part of the boundary that I called big B, then we can still recover a large part of the bulk. We can recover the so-called entanglement wedge, everything to the left of that dotted line, so-called little b. So in particular, you have some qubit sitting in the center of the bulk, some like spin that could be up or down, and there's some operator you want to apply to that spin. And from a boundary perspective, we can apply that operator just by acting within this region big B. So it'll be some very non-local operator, but it will only be non-local within the region big B. So this is one definition of quantum error correction. It's not the most common definition within the quantum computing community. It's the so-called sort of Heisenberg picture definition, thinking about operators rather than states. But the idea is that for any operator, I've made it a unitary operator here, u little b that acts within this bulk region little b, then there's a boundary unitary u big B, such that u big B acting on v of psi is the same as v acting on u little b psi for any state psi in this bulk effective field theory Hilbert space. Okay. Okay, so any questions about that? Because that was just a lightning review of the standard story in ADS-CFT, but I think it's important to have everyone on the same page before we go on to the more radical stuff with black holes. Okay, nobody is shouting up as far as I can tell, so I will go on. Okay, so what changes when you have a black hole? Well, it's something sort of pretty obvious that has been said many times over the years in increasingly precise ways. But the basic point is that if you look at a black hole that's been evaporating for a long time, or even just sort of sitting there for a long time, then it contains a very long interior. The interior just grows at roughly the speed of light, effectively, over time. And so you have more and more degrees of freedom in the interior. And eventually, you get to the point where there are just more low energy effective degrees of freedom in the interior of the black hole than there are fundamental degrees of freedom that describe the black hole. If we believe in the so-called central dogma that the number of degrees of freedom describing the black hole is given by the Bekenstein-Hawking entropy. Okay? And the trouble with having more effective degrees of freedom than you have fundamental degrees of freedom is that this old story from ADS-CFT, where you have an isometric map from the effective theory to the fundamental microscopic theory, whatever that might be, just can't be the case. Okay, because you can never have an isometry from a larger Hilbert space to a smaller Hilbert space. There's just not space to fit a complete basis of orthogonal states into the smaller Hilbert space. Okay, so essentially, if we want to still have quantum code, we still want to have a linear map from effective field theory states describing the interior into fundamental states, whether those be boundary states in ADS-CFT or whatever they're meant to be in flat space, so on, the fundamental microscopic states of the black hole, then we simply have to allow V to be non-isometric. There's no other way around it. You just can't have an isometry from a larger Hilbert space to a smaller one. In particular, this means the inner products in the fundamental Hilbert space are no longer the same as they were in the effective field theory Hilbert space. This may seem pretty bad, but I'm going to argue to you that even though it's a pretty radical change from what we're used to, then it's not totally catastrophic. And in fact, within the effective theory, you can't tell that it's happening at all, even though the real theory is related to the effective theory in a highly non-isometric way. Okay, and I'm mainly going to argue this to you by thinking about a very simple toy model that the close variants of this have been studied by people before. It's very closely related to sort of random tensor network models and so on. But the idea is that we're going to have a mapped V from our larger effective field theory Hilbert space describing the black hole interior into the fundamental microscopic qubits describing the black hole. And this map is just going to be very simple. We're first going to apply a unitary U to our effective field theory qubits. And I'm going to assume that this U is sampled from the half random ensemble. Okay, just because that makes calculations very easy. And, we expect black holes to be chaotic, random looking objects. So this is supposed to be a simple but crude model. But I want to emphasize here that we're not physically going to be averaging over the Haar random ensemble. We're not doing some gravity ensemble duality here, like in JT gravity. We're just imagining there is some fixed but random looking pseudo-random U that's been drawn from this Haar random distribution at random. We're going to use the statistics of the Haar random distribution in order to learn stuff about typical U's, but we're not actually physically going to be averaging over. Okay, so after applying this U, we still have too many qubits. So what's the only way you can get rid of qubits? Well, basically, you've got to do a projection. Okay, so what we're going to do is we're just going to project a load of qubits into a fixed state that I call the zero state for simplicity, until we have a small enough number of qubits to describe the microscopic states of the black hole. And then that's going to be our fundamental Hilbert space. Okay.
Is there just by Amazon.
I think somebody might need to.
Oh yeah, I just assembled it, but I'm not sure whether I can correctly assemble. So I just.
Oh, I can mute it. Okay, they're muted. Okay. Great. So in fact, any V, it turns out, can be written as a combination of a U and a projector. So this is a pretty general thing to consider, though obviously making the U be Haar random is a choice. But this is some non-isometric map, and it has an output dimension that's much, much smaller than the input dimension. And so in principle, there are lots and lots of states that just get annihilated by this map, and the kernel of this map. That means that it's very highly non-isometric inner products, in principle not preserved at all. And by the way, I did miss out one thing here, which is let's call the number of qubits. Sorry, the number of qubits getting projected here, NP. Then I'm going to have a prefactor at the front of 2 to the NP. Okay, that's just going to be, sorry, NP over 2. That's just a normalization factor to make sure that typically stay normalized by this map. Okay, but don't worry too much about that, but I thought I should get it in there. Okay. So the idea is that even though the output Hilbert space is vastly smaller than the input one, it's very hard to tell that just by looking at example states and seeing the inner products of example states. So in fact, it turns out that typically the inner product between any two states, psi and phi, the inner product from the fundamental description, so graph phi, b dagger v, ket psi, is going to be equal to just the inner product in the effective description, inner product of phi and psi, plus some exponentially small correction. It's exponentially small in the number of fundamental qubits. The fundamental description, i.e. exponentially small in the Bekenstein-Hawking entropy of the black hole. So it's non-perturbative in G. Okay. So this is a statement about just the sort of the standard deviation and so on. It can be computed very easily by doing so-called Weingarten calculations. If you're familiar with how to do integrals over Haar random unitaries. I'm not going to go through that in detail, but it should be obvious to those familiar with it. Otherwise, you can look in the paper. But it turns out there's a much stronger statement you can make that uses some more powerful mathematical tools called measure concentration. Uses a generalization of so-called Levy's lemma, if you're familiar with that. Again, you can look in the paper for how this works, but it actually gives you a very, very powerful statement that says that the probability of the inner product in the effective description being more than epsilon different from the inner product in the fundamental description is doubly exponentially small. So you'll see it's exponential in 2 to the number of qubits in the fundamental description times epsilon squared. So if epsilon is like small but not too small, then this is still doubly exponentially small. Okay, that means it's incredibly rare for 2 states to not have their inner product preserved. Of course, there still are some states that the inner products are totally different in the fundamental and effective description. For example, there are all the states that just get annihilated by V, then their inner product will be 0, but it will be very non-zero in the fundamental in the effective description in general. Okay, so this is not a statement about all states. There are doubly exponentially many states in the full Hilbert space, so it's perfectly consistent for the probability of it being different to be doubly exponentially small, but there still will be lots of states where it isn't small. So you might say, okay, we just have to prepare the right state, and then we'll be able to see that these inner products aren't preserved, and everything will still catastrophically fall. But the issue here is that not all states are equally practical to prepare while remaining within the effective field theory. Okay, and particular the complexity of preparing an arbitrary state, the sort of number of steps you need, the length of the quantum circuit, the set of unitaries that you use to prepare it, will in general be exponentially high. Okay, and that will take exponential time to do, and we don't really believe in effective field theory over exponential times. Like there's all sorts of arguments you can make that states with exponential complexity you can't necessarily trust effective field theory calculus. Basically, you can have an exponential number of exponentially small corrections, the effective field theory, and that could just cause the whole thing to break down. Okay, so suppose we just restrict ourselves to states with sub-exponential complexity. So states that can be prepared from some particular simple state by some sequence of simple unitaries, so unitaries that act only on a couple of qubits at a time. And that sequence is going to consist of a number of unitaries that's sub-exponential in n fundamental, in the Bekenstein-Hawking. Okay, so that's a very reasonable physical consideration of the sort of states that we could actually prepare. In fact, it's a lot more than we could ever actually prepare, but we want to allow some pretty complicated things like allowing black holes to completely evaporate and so on. But it's roughly the reasonable condition before we expect all hell to break loose. Okay. So how many states are there with a complexity less than or equal to some number c? Well, you have some set of simple unitaries that you can apply that grows maybe polynomially with the number of qubits you have to apply them on, but doesn't grow very fast. So roughly the number of states with complexity c is just exponential in c. Okay, there's some prefactor that depends on how many unitaries you include as simple, depends on details, but sort of independent of details, you'll get some answer that's exponential. Okay, so then we can consider the probability that any state with complexity less than or equal to z will have, any pair of states even, will have an inner product in the fundamental description that is significantly different than their inner product in the effective description. Okay, and there's a very crude bound that we can put on this, which is just to say that this probability is upper bounded by adding up the probability that each pair of states with complexity less than c has an inner product that's very different in the fundamental and effective description. Okay, so it's the probability for each individual one times just the number of different pairs that there are that both have complexity less than or equal to c. The number of pairs grows exponentially with c. We just said that. And I also claimed that based on measure concentration, the probability for each individual pair is doubly exponentially small in the Bekenstein-Hawking entropy. So what this means, it means that this very crude so-called union bound still tells us that the probability of any pair of states being able to detect the change in the inner product, any pair of states complexity less than c, is always going to be very, very small, just so long as c is sub-exponential in the Bekenstein-Hawking. So we can really allow very, very, very high complexity states, and they still won't be able to learn anything about the changing in a product for typical Bs, for almost all Bs, you know, where we've chosen U according to the higher random answer. Okay, and this is really a very powerful result. Measure concentration is an extraordinarily powerful thing. If you don't know anything about it, I encourage you to read about it. We have a long pedagogical appendix explaining, you know, how it all works in our case, you know, giving some very general statement of measure concentration. But it's a really, really cool and powerful thing. And it does give us this very powerful result that not only are most states unable to detect the difference between the fundamental and effective descriptions, but almost always no sub-exponential complexity ones. Okay. So there's another consequence of this that's pretty powerful and important. And that's that if we have some fundamental state phi that is equal to V of psi for a sub-exponential complexity state psi, then that psi will always be unique. Okay, and the reason for that is that if we had two different states that were both mapped to the same fundamental state phi, then inner products would not be preserved. Okay, it's pretty simple to see that that's true. And so if we have a sub-exponential complexity state in our fundamental description, then it will have a unique effective description. There's no ambiguity in the effective description until you get to these crazy high complexity states where we shouldn't even believe in the effective description. Okay, so this all should be starting to give you a feeling that, okay, maybe this thing can sort of hold together. Maybe we can still have a meaningful effective description of what's going on, even when V is highly non-isometric. But I'd also want to talk briefly about error correction in non-isometric codes, because that was a pretty important part of the usual ADS CFT story. And you know, the sort of meaning of the bulk was that and localization in different regions of the bulk was that it could be error corrected from different parts of the boundary. Okay. So a very fundamental fact is that you cannot do quantum error correction in the sort of true quantum computing sense for any non-isometric code, even if you're not erasing any part of the boundary. So even if no boundary qubits, no fundamental qubits get erased, even if you have entire access to the entire fundamental description of the state, you can't do proper quantum error correction of the full logical state of the effective theory state. And the reason is very simple. It's that if we could do quantum error correction of the effective field theory state, then we'd be able to get back, look at the physical state, do some physical operations, some linear maps, and be able to recover the logical state. That's one definition of what it means to do quantum error correction. But it's sort of obvious that that's impossible because a map V from a much larger Hilbert space into a much smaller Hilbert space is always non-invertible, right? There's just no way to get back where you start. Okay, so we don't have quantum error correction in the sense of Almiri, Dong, and Harlow. But it turns out that there's a weaker version of quantum error correction called state-specific quantum error correction that was first introduced in the context of ADS CFT in a paper I wrote with Patrick Hayden. Its most precise form was introduced by me and Chris Akers. There was also earlier things that are very closely related, state-dependent mirror operator reconstructions of Papadopoulos and Raju that are very similar in spirit. And this is a sort of weaker condition than being able to do true quantum error correction. But the idea is that, so if we go back to the definition of quantum error correction before, all the way up here, the idea was that any bulk operator, we could find a boundary operator that did the same thing. Okay, and that boundary operator had to do the same thing for all bulk states. Okay, all that we're going to change now is that it's only going to need to do that for one particular bulk state psi. In other words, we're going to allow our reconstructed operator that acts on the boundary to not only depend on the bulk operator that we're reconstructing, the effective theory operator that we're trying to implement, but also on the state psi of the effective theory that we're trying to act on. Okay, And unlike true quantum error correction, unlike traditional quantum error correction, this sort of quantum error correction can exist for non-isometric codes. And in fact, it happens in really very interesting ways in non-isometric codes. So I'm going to illustrate that with an example. And the example is going to be an evaporating black hole after the page curve time, and this idea that you have an island, an evaporating black hole, late time, a part of the interior that's going to end up encoded in the Hawking radiation. Okay. So how are we going to describe a late time evaporating black hole within this toy model of the black hole as a non-isometric code?
Sorry, Geoff, can I ask a question?
Yes, go ahead.
So I think you have this nice isometry which relates the effective field theory description and the microstate. But
yep.
Can we think also? I mean, I think you have in mind island prescription, but can we think some also similar projection, like proper projection, like model appears also final state projection, I mean, black hole final state. Do you think there are such an interpretation?
Yeah, it's good. So the question is how this relates to the early ideas of Horowitz and Maldacena and so on about final state projections and the idea that the black hole singularity projects onto a certain state, and that's how information gets out. Mathematically, it's obviously very closely related. We're both having a projection, and that's sort of how the information is going to get into radiation. I think the interpretation is pretty different. We're not thinking of this as happening at the singularity, and we're thinking of it, this is sort of happening the whole way through the process as the black hole's evaporating, and it's more related to the fact that you have a horizon rather than the singularity. It is possible, it's still possible that it should be thought of as happening at the singularity. So also they're thinking of it as a physical process that happens. We're thinking of it as a mathematical way to relate two different descriptions. So I think the interpretation is pretty different. I think there's obviously reasons you want to put it at the singularity, because the singularity is mysterious, and this is kind of mysterious, and you put your mysteries together, and then there's one less mystery. But there's also reasons why it's a bit problematic to have it be at the singularity. So the state that you project on is much less natural if it happens at the singularity, because it has to sort of undo all the dynamics that happen between the horizon and the singularity in order to sort of give the right answer for the right final answer. So I think there are issues with making the original final state story work, but clearly in spirit there's and sort of inspiration and so on, there's a huge amount of connection and yeah.
Thank you very much.
Yeah. Okay. So what is our effective description of the old black hole? Well, we have a load of Hawking radiation, a load of qubits. Okay. And those are entangled with stuff in the interior. So there's a load of other qubits in the interior that are entangled with the Hawking radiation. And then there's some other qubits in the interior that maybe describe infalling modes into the black hole that aren't entangled with the Hawking radiation, just in some state. I just drew one here that represents a diary that's been thrown into the black hole. That's just to keep things simple. You could have other stuff in there as well. Okay. And now we want to see how that's related to the fundamental description. So the Hawking radiation is far from the black hole. Nothing happens to that. That's, there's no crazy holographic stuff going on there. There's no issue with more qubits in the effective description than in the fundamental description. It's just some very low density. Maybe it's even escaped into a non-gravitational bath. There's no crazy stuff going on there. So that just stays exactly the same. But the interior gets mapped into the black hole microstate degrees of freedom that I've called B. Okay. And it gets mapped by this non-isometric map, right? So a Haar random unitary and then a projection. Okay. Okay. So in the effective description, we just have a state that I called psi I, where all the Hawking quanta are in the Hawking state, they're maximally entangled with their interior partners. And then there's the diary, which is in some state that can call ket I, if you like. Okay, this represents an arbitrary state of diary. So we have different states of diary. And if the diary is in orthogonal states, then the effective description is an orthogonal state. The diary is just a subsystem of the effective description. In the fundamental description, we have V acting on psi I. Okay, so this unitary has been applied to the interior, and then the projection has happened to reduce the number of degrees of freedom. Okay, and the interesting thing is that even though seemingly nothing has happened to the Hawking radiation here, the Hawking radiation will no longer be in a maximally mixed state. And there's a really easy way to see this, which is that the only thing for the Hawking radiation to be entangled with is the black hole microstates, big B, and there just aren't enough of them for the Hawking radiation to be maximally mixed. So the entropy of the Hawking radiation has to be at most big B. It has to follow the Page curve because it's still a pure state. This map V, map pure states to pure states. So even though V didn't do anything to the Hawking radiation, it still has changed its state. Okay, and this is, I think, slightly confusing to people. Initially, it's really very simple. Why would we think that the Hawking radiation would be in the same state for before and after we applied V? Well, it was because V didn't act on R. So if we have the trace over big B of V psi ket psi bra psi V dagger, then V only acts on B. And so we can move V dagger around the end. We can use the cyclicity of the trace to get something that's, this is slightly wrong, that's the trace over the interior degrees of freedom of V dagger V times ket psi bra psi. Okay, and normally V would be an isometry, and then V dagger V would be the identity, and then we'd see that this is the same state as the trace of the interior of the effective description, just ket psi I bra psi I. Okay, but if V is not an isometry, then that's just not true. And in fact, for the V's we're considering, then the resulting state of the radiation, its entropy will just be very different for the two states. Okay, so there's no reason they should be the same in the two descriptions of the state. So another interesting point is that the fundamental state, V psi I, I'm just going to claim this to you, but if you've studied tensor networks and so on, it should be kind of obvious. This fundamental description state up the top here will always be maximally mixed on big B. Okay, big B will be maximally entangled with big R, and that is true. So that's saying that the Page curve holds, but that will be true regardless of the state of the diary. It will be true for any state psi I. Okay, so what does that mean? Well, if I have any two states that are maximally mixed on big B, then there must be some state, some operator, UR, some unitary operator acting on the radiation that maps one into the other. Okay, this is just the statement that any two purifications of the same density matrix are related by a unitary. Standard statement in quantum information. And so that means that any unitary acting on the diary, we can always find a unitary acting on the radiation such that UR acting on V of psi I equals V acting on U diary psi I. Okay, so we can find a UR that does state-specific quantum error correction of the black hole interior using just the radiation. So we've traced out all the output of V, and yet we're somehow still able to reconstruct the input to V just from the reference system that the input to V was entangled with. Okay, so this is a radical new quantum error correction feature that would never be possible with isometric codes, but it can happen with non-isometric codes. And this is, of course, the famous island that we have in quantum gravity after the Page curve. Okay, this is the island in the black hole interior. It's a toy model version of it. But we're now understanding very explicitly the sense in which this radiation, which is just potentially some QFT state in a bath somewhere, nothing to do with gravity, is able to secretly encode the interior of the black hole. It's very far away. Okay. So Jeff, one comment.
Yep. Excuse me. don't you want to say that the UR doesn't depend on the state of the diary? So you call it state specific, but you should have the whole family of states differing by the state of the diary, considering the rest fixed.
Yes, so we can do better than just have it work for the one state psi. We can have it work for the whole subspace of states where the interior partners are fixed to be entangled with the Hawking radiation, but the diary is allowed to be in any state. So it's still specific to a certain subspace, but it's more than just the one pure state psi. I was just keeping things very simple. But the important point, if we just had an arbitrary state where any of the qubits can be in any state, then we wouldn't be able to reconstruct the diary.
Well, making it so simple by only talking about one state is confusing in another way, because quantum mechanics has little content if you restrict to one state.
This is true. But there's also, it also in some ways allows you to talk about more general stuff. But I agree that in some ways it's simpler to think about. Okay, so the story I would have told a couple of years ago is just to think about code subspace just consisting of the diary, and then sort of not really consider all these other degrees of freedom at all, and then say, for that code subspace, then we have ordinary quantum error correction. But that's doing a disservice to these other degrees of freedom, which are just as real effective field theory degrees of freedom as the diary. So that's why I think it's better to say that they're really there, and just that you can't do full quantum error correction. You have to rely on at least being partially state specific. And yeah, so one way to think about it is to say that what you're wanting to talk about is state specific reconstruction, where the diary Hilbert space is maximally entangled with some other reference system that you're not allowed to do the reconstruction. Then you just have one pure state, but it's really giving you a whole subspace of states. We can maybe talk about this offline. I agree that there's advantages to code subspaces, that it's kind of confusing when you only have one state, but there's also advantages to being more specific. Okay, so one comment that I wanted to make here is that it might be confusing here that UR is also an operator that just acts in the effective description, right? Nothing has happened to the radiation in the effective description, and we're just applying some UR over here, and yet I'm claiming it's doing the same thing as the U diary acting on the diary degree of freedom, which is an independent degree of freedom in the effective description. Okay, so that's sort of paradoxical within the effective description, but that's fine, and it's fine because it turns out that U big R will always be exponentially complicated. And we've already decided ages ago that the effective theory can only be trusted, that it only sort of makes sense to talk about for sub-exponential complexity effective states. So you can't think about this UR as being an operator that acts within the effective field theory because it's too complicated. You can think of it as acting on the radiation in the fundamental theory, or you can think of it as doing the same thing as U diary in the effective theory, which is some simple operator. But you can't think of it as just an operator on the radiation in the effective theory, or the effective theory will break down on you. Okay, and you'll start, the fact that V is not an isometry will come back to bite you, and you'll get wrong answers. Okay, so that's an example of the things that this non-isometric V is costing. Okay, so how am I doing on time? Yep.
Excuse me, can I ask you a question?
Yep. Yes.
How is it different from operator pushing?
This is the same thing as operating pushing. You can, one way of physically finding this UR would be to do operator pushing, sure. The thing I want to emphasize, normally we think of operator pushing as going through the sort of in-plane legs of a tensor network. And here we're pushing it through a bulk state. That's the only difference. So mathematically, you can still do operator pushing here and it will work fine. And that's one way to see that this UR exists. But there is a new interpretation that's going on here, and you're relying on the bulk state being a certain state in a crucial way that we weren't, you aren't in the sort of traditional stories about tensor network.
Okay, thank you.
Okay, so one thing I haven't really talked about is where the QES prescription comes in here. And so what was happening with the QES prescription? Well, we're somehow doing a computation in the effective description that eventually gives us the answer that is not computing the entropy in the effective description. It's computing something else. It's computing a extremization over area plus entropy. And then we get an answer that's magically the entropy in the fundamental description. Okay, so this is a sort of confusing thing, how it's able to do this. It turns out there's a paper Chris Akers and I wrote last year, building on seminal earlier work by Dan Harlow in 2016, that for any quantum code, non-isometric or non-isometric, then anytime you have complementary state-specific quantum error correction, and what I mean by that is basically everything in the effective theory that's not reconstructed by R is instead reconstructed by B. Okay, or anytime you split into two boundary regions, anything not reconstructed by one is reconstructed by the other in a state-specific way. Then you also have a QES prescription for entanglement entropy. And what I mean by that is that there will be some formula that looks like minimizing over some quantity that you can call area plus effective theory entropy, and that will compute for you the fundamental theory entropy. So in our case, what you get, and you can again compute this very explicitly using Weingarten stuff, pretty easy to do, is that the entropy of R for the state, the radiation, Hawking radiation R for the state V of psi, that's for the fundamental state of the system, given by the minimum over the entropy of the radiation R in the effective field theory state, and the number of qubits in B plus, that's roughly the area of the horizon, plus the entropy of R plus everything in the interior in the effective theory description of the state. Okay, so this is exactly the quantum extremal surface prescription, or the island rule. This is just the first possibility is just the semi-classical entropy of the radiation. The second possibility is the horizon area plus the semi-classical entropy of radiation plus interior, right? Entropy of like radiation plus the island. Okay, and this hopefully makes it very explicit. People, at least back in the day, were sort of confused about how, you have the entropy of the radiation being computed by some formula that itself involves the entropy of the radiation, just a different entropy. Okay, these are just entropies for two different states. One is the entropy of the state that is the effective description of the real state, and one is the entropy of the real state itself. And those are different because they're related by non-isometric map. Okay, so I'm running short of time, which is great because I'm just gonna end on some final comments about, okay, how is this meant to have helped you? Really the goal of this paper is to just be as clear and explicit as possible about some of the confusions that existed post 2019. And I think I want to emphasize that a lot of this stuff was at least to a greater or lesser degree understood by the people writing the papers back then. So we're just trying to really, spell everything out as explicitly as possible and make everything free. But just to be very clear, so the QES prescription that gives you the page curve is really computing an actual entropy. It is the actual fundamental entropy of the Hawking radiation. It's just that we're computing the entropy of the fundamental state, and we're doing that using the entropy of the effective field theory state. And those are different entropies, not because anything is actually happening to the radiation. V is not doing anything there, but because a non-isometric holographic map is encoding the effective description of the interior into some black hole microstate. Okay, and that's where all the work is being done. It's in the relationship between those two descriptions, the effective description and the fundamental description. And in particular, again, I want to emphasize there's no non-local dynamics going on here. There's somehow moving information out of the interior, no non-local Hamiltonian, anything like that. In the effective description, the information just stays in the interior through the whole evaporation process. Unless you do something exponentially complex that makes that effective description break down, then that will just always be true. Up to exponentially small corrections from wormholes or whatever, then the information just is in the interior. In the fundamental description, on the other hand, the information is always in the radiation, or at least once it gets emitted by the black hole, it's in the radiation. But it was never in the interior because the interior doesn't exist in the fundamental description. The fundamental description, you just have whatever microscopic qubits make up the black hole. Okay, so that's really the distinction there. And I again, just to advertise why you guys should read the paper, or at least look at a figure from the paper. In the paper, which I haven't had time to talk about, we describe a sort of very concrete dynamical toy model where you have an effective description, you have a local fundamental description, you have time evolution in both. In both cases, the time evolution is local, or in the fundamental description, it's like k-local, or acting on k-locally on the microscopic qubits, the black hole. There's nothing coupling to radiation far away from the black hole. That's just free streaming, a free QFT, free lattice theory. And we have a holographic map V relating the two. That map is equivariant with respect to time evolution. As in, if I do time evolution in the effective field theory, it's the same as time evolution in the fundamental theory. And just everything's consistent, and the information escapes in the fundamental description. It's in the interior in the effective one. And yeah, there's no problem. So yeah, possibly I copied this figure from the paper, but this is how it works. I'm not going to go into details. You can look it up. But stuff in the effective description, stuff falls in the black hole. There's some unitary dynamics. Stuff gets emitted, and to construct the map V, we basically just bend some arrows around to turn that into a map that takes an effective description Hawking state into the same state that we had from the fundamental description. So it's sort of by construction, it's all consistent. But yeah, I think I'm just going to end there because I have rather run over on time. So thanks a lot.
Yeah, thank you. Any questions or comments?
Sorry, can I ask a question?
Yep.
So in your this isometry map, you project down to, I think, direct product state.
It doesn't matter. You mean this state is zero?
Is that any state arbitrary. Projection?
But because the U is how random here, then any state is equivalent. The more physical one is this dynamic model down here, and there what we're effectively doing is projecting onto maximally entangled states between it's projections onto maximally entangled states that basically project the interior partners in the Hawking mode and the information that's meant to be coming out in that Hawking mode into a maximally entangled state. It's the same, in many ways, the same construction that was done in, I think Horowitz and Maldacena did it, certainly like Preskel and was it Dan Gottesman, their paper, they were doing this. It's the same stuff, final state people did, but again, the interpretation is different. We're wanting to think of this as two descriptions that are both simultaneously describing the same physics, rather than like you first have this state and then there's like a physical dynamics here that happens, and then afterwards you have a new state.
Also, could you give us some rough sketch for why you have this two minimum of this two quantity like island formula and follow in the computational entropy?
Yeah, I can give a couple of answers to that. So just within this time model, then the answer is just you have this half random unitary and you do a replicative calculation and you have a sum over permutations from the usual sort of Weingarten calculus. And that gives you two terms, and one of them will dominate for the Rayleigh entropies, and then you analytically continue the dominant one, which is the smaller of the two. So it's just the usual story about how you get like RT from a random tensor network. the more general story that says this is true for the theorem I was referencing here, that I was is sort of a more, it's a much more general, more powerful statement, just saying that any time you have this sort of complementary state-specific reconstruction, then there's always, there's a certain definition of area that we give in that paper with Chris. You can look it up, but I'm not going to go into details of it, such that the entropy is always given by a minimization of that area plus entropy over all possible bulk regions. So in this case, I just wrote 2 down, but really in this theorem, we would be minimizing. So we have here, we have a load of qubits in the interior. We'd be minimizing over all sets of qubits in the interior, and we'd have a different area associated to each one, and so on. It's just because this is very simple, then it will always only be one of these 2 options that dominates. Right? It's like,
it's related to some 2 different ways to cut to this tensor network diagram.
Oh yeah, so roughly one is a cut above U and one is a cut below U. Is one way to think about it. Yeah. Yeah, that's the 2 different terms. That's the just explicit, simple to calculate thing.
Thank you very much.
So any other questions or comments?
Sir, I have a question. Am I audible?
Yep.
Okay, so does the incoming diary or whatever object have to be pure? Could that also be maximally entangled to some other state before entering the black hole?
Yeah. So this was what I was talking about to Edward. So yes, in fact, as long as it's not too big, then it can be in any state. But if the diary was like really, really big, and it was highly entangled with some other thing, then you might not be able to error correct it anymore. So it just depends on how big it is. Roughly, it depends on whether or not it's in the entanglement wedge. So if I make the diary more and more entangled with something that's outside the entanglement wedge of R, then it will increase the entropy of the island, but it won't increase the entropy of not having the island. And at some point, the entropy of having the island will be bigger than the entropy of not having the island, and then the island will disappear and you won't have an island anymore when you do the QES prescription. And that's the point where you won't be able to reconstruct the diary anymore.
Thank you.
Any other question? So yeah, so let me ask one thing. So for this non-isometric code, sorry, I'm not familiar with it, but in order for the recovery channel to exist, I mean, is there any kind of Neal-Laflamme type condition?
Yeah, the Neal-Laflamme ones are, as I say, you can't have proper quantum error correction with a non-isometric code, just because the output is too small to encode the input properly. And so you don't really have Neal-Laflamme. Fully general state-specific reconstruction, then I don't know a clean equivalent of the Neal-Laflamme conditions. If you think about some code subspace, you just fix everything except for 1 degree of freedom. You say what Edward would want you to do. You say that all of this diary is an arbitrary state, but all of these are in the fixed state. And then you can just think about ordinary quantum error correction of this diary from the fundamental description. That map is actually an isometry, even though the map including these extra degrees of freedom is not, or it's very close to an isometry. Okay, and so then you can use ordinary Neal-Laflamme stuff if you want.
Yeah, that's true.
So that's the story you can do. But as I say, I think it is better to treat these extra degree of freedom with respect and include them in your effective description, because then you can do more stuff and still tell a compelling story. It's just a bit more complicated.
Okay, thank you. Any other questions or comments? So maybe, it's better to move on to the next talk. So let us thank Jeff again for the nice talk.